Mathematics made easy, no more fear. Target online class, we got you. Wherever you want it from, we got what you need. Target online class.
Good day, viewers all over the world. You are welcome to Toidel online class. So today we want to look at Cosets and Index. Cosets and Index. Of course, we have defined a subgroup. We know the meaning of a subgroup. When we have a group, we know how to define a subgroup from a group. So we want to look at cosets now. We want to look at cosets and index. So now let's see the definition. If H is a subgroup, if H is a subgroup of a group G, if H is a subgroup of a group G, and A is an element in that group G, H is a subgroup of a group G, and A, that element A, belongs to that group G, then the set HA, that is, this is the subgroup and the element, which is defined as the element H. A, this element H, this small h is from H, is from this subgroup, and A is an element from G. Then the set HA, such that H belongs to H, is called the right coset of H. That is, if the element from G is coming, is by the right hand side of the subgroup, is called the right coset of H. And the set AH, that is when we have the element from G, which is at the left hand side of that subgroup, AH, it is called the left coset of H. So when you talk about coset, the coset, it could be either left or right, as we have it on the board. The element A is from the group, while the small h is from the subgroup. So if you have the product of the two, depending on where the element A is, if the element A is at the right hand side, it is called the right coset of H. And if the element A is at the left hand side, it is called the left coset of H. So that's how to define a coset. Then there's this other concept that we define, which is called the index. How do you find the index of H? The index of H in G, that is the index of the subgroup in the group, is the number of distinct right or left coset of H in G. That is, when we find the coset, either left or right coset, then from there we can actually know the index when we have the number of distinct coset that we have of H in G. So two rights or left cosets are either disjoint or identical. We are going to see that when I give example. When we have either two right or two left cosets, they can either be disjoint or identical. So we are going to see that by the time I give example. But I want us to understand the concept, coset and identity. What is called a coset? In case of a coset, it can either be left coset or right coset. Then the index simply means the number of distinct either left or right coset of H in G. So I will use example to explain, to buttress the point further. So let's take example so that it will be clearer. Let me use example to explain further. Let's see example. Let's look at example. Let's this be the first example. Example 1, where we have consider the group. Consider the group Z6 under addition and the subgroup H with Z6 equals 0, 1, 2, 3, 4, 5. That's what we have. And H is equal to 0, 2, 4. So of course, H is a subset of that Z6 as we have it in the example. H is a subset of that group 6. So the first question now is that we have to write down the left coset of H. Of course, we are going to do the left. Then at your own leisure time, you can go ahead and do the right. Still the same thing. It depends just the element from the group. When you place it by the left, is the left coset. When you place it by the right, is the right coset. So you can do that on your own. Then the second one is, what is the index? What is the index of H? The index of H. So this is the problem. This is what we want to solve. So let's look at it very well. This is in this case now, this is the group G. This is the group and this is the subgroup. We want to find the left coset. So the first one now, you say the left coset of H are given as AH. That will be AH, given that H belongs to H. That's what we are going to have. The left coset simply means the element A that is coming from Z6 will be at the left hand side of the subgroup. If it is the right now, if you are asked to find the right, it will be AH. That is, that one will be HA. H belongs to H. This is the right, but we have to find the left. So the element A, the element coming from this Z, will be at the left hand side. If you have to find the right coset, you place that right hand side. So it's still the same thing. Just try and understand the question. Just try and understand the question. We have to find the left coset, and this is what we are going to do. So we are going to pick these elements one after the other. Solution. So we now continue to pick the elements. Let me clean this place. We pick the elements one after the other. There are 6 elements there. You know, we have AH being H belongs to H. This is what we have. So this is what we have. So we now pick the elements one after the other. The first element there that we have is 0. We say is 0H. This same thing as is 0 plus H, because it's in the question is Z plus is Z, that's Z6 is under addition. The binary operation there is addition. Please check the question. Is Z6 comma plus. So the binary operation there is under addition. So what will this give us? No, let me write it neatly here. Under 0H, I'm going to have 0 plus H because it's under addition. Then this will give me, you know, H has 3 elements. H has 3 elements, 0, 2, and 4. So I'm going to have the first one will now be 0 plus 0, comma 0 plus 2, comma 0 plus 4. At the end of the day, what do we get? We are going to have 0, 2, 4. That's the first element. A are the element of Z6. So then we have 1H. What would that give me? 1 plus H. And that will be 1 plus 0, 1 plus 2, 1 plus 4. And this is going to give me 1, 3, 5. Please look at it very well. Any question? If you have any question, just write at the comment section. Any question? Look at it very well. A are the elements. They are the elements of Z6. And they start from 0 to 5. So please look at it very well. So I'm picking the element one after the other. But we are doing the left coset now. So at your own leisure time, you can do the right coset. So we are doing the left coset now. So I'm picking the element of Z6. No, I've rubbed it off, but it's there. The element of Z6. Then 2H. So 2H, what do we get? That will be 2 plus H. Z6, that Z6 is under addition. The binary operation there is addition. That's what I'm adding. If it is multiplication, you multiply. So here we are going to have, in this case now, I'm going to have 2 plus 2. 2 plus 0, 2 plus 2, then 2 plus 4. So here I'm going to get 2. I'll get 4. But look at this is 2 plus 4. 2 plus 4 is 6. You know it's under side 6. 6 divided by 6 is 1. Remember 0. You write this remainder here. Please check what I've done there. Any answer that we're going to get must not exceed 5. It must not exceed 5 as we have it in the element. So when we have 3h, it will be 3 plus h, and that will be 3 plus 0, 3 plus 2, then 3 plus 4. So here I'm going to have 3 plus 0 is 3, 3 plus 2 is 5, then 3 plus 7, 3 plus 4 is 7, 3 plus 4 is 7, 6 is 7, 1, remainder 1, so here will be 1. Then where we have 4h, we are going to have 4 plus h, and that will give us 4 plus 0, 4 plus 2, 4 plus 4. Then here I'm going to have 4 plus 0 is 4, 4 plus 2 is 6, 6 is 6, 1, remainder 0, then 8, this will be 2. Please look at it very well. If you have any question, you can just write at the comment section. No, the addition part I'm talking about. No, in this case now, we are given Z6 addition. That's what we are given in the group. That's the group. The group is given as Z6. Then the binary operation there is addition. That's why we are adding. What I'm trying to say is that, what if, this is what I'm trying to say. What if you are given that Z6 under multiplication? That's what I'm trying to say. If the binary operation is multiplication, we can't talk about a group when we don't have a set and the binary operation. For us to be able to talk about group or subgroup, there must be a set and there must be binary operation beside it. Most of the time we use asterisk. Asterisk could be anything. It could be addition. It could even be union. It could be intersection. So asterisk could be anything. What I'm trying to say is that in this question that we are solving now, the binary operation given is plus. That is why we are adding. What if it is multiplication? We are going to have OH here. We are going to use this to multiply, not addition, not to add. That's what I'm trying to say. So you check the binary operation that we are given. It is that binary operation that will determine what to do. But in this case, it's addition. That's why I'm adding. If the binary operation is multiplication, we multiply. Then the last element there under Z6 is 5. So here we are going to have 5 plus h. So that will be 5 plus 0. We have 5 plus 2. We have 5 plus 4. So in this case now, 5 plus 0 is 5. We are on the silver side. 5 plus 2 is 7. 7 minus 6 minus, when you take 6 from 7, we have 1. That's left over. Is Z6. So any answer that we are going to get must not be 6. It must be less than. Then 5 plus 4 is 9. 9 minus 6, that's 3. We're going to have 3. So this is we have given the left coset. So this is the first part of the question. This is the left coset. The left coset of H. Then the second question, we are asked to find, we have to write what is the index of H. What's the definition of index? We said the index of H in G, when we started this topic, is the number of distinct right or left cosets of H in G. So now let's look at how many distinct cosets do we have here? This one 0 to 4. Under set we don't really deal with arrangement. As long as the element is there, either the element is repeated or not. If it's under set, we don't really, the arrangement does not really matter. 0 to 4, this is a pattern. 2, 4, 0, it still has 3 elements, 0, 2, and 4. Then this place also the same thing. So these are distinct. 1, 2, 3, they are the same. Let's check another distinct element that we have there. That's 1, 3, 4. 1, 3, 5. 3, 5, 1 is still the same thing. There are 3 elements. Then, so how many do we have there? B. The second question now. Write down the index of. So there are, just say there are 2 distinct cosets. So the index of H is 2. So that's how to answer that second question. So if you look at it, there are 2. There are just 2 distinct cosets. As we have it, to be 0, 2, 4 or 1, 3, 5. Those are the 2 that we have there. Please check it very well. Oh, somebody is asking, why do I stop at 5H? Look at Z6. Z6 under addition. The elements start from 0, 1, 2, 3, 4, 5. Where A, please just look at where A, this A are the elements of the group. In this question now, the group is Z6. Why the subgroup is H? Please look at the question. I've rubbed it off on the board, but please look at the question. I stopped at 5H because 5 is the last element under Z6. Z6. There are 6 elements there from 0 to 5. That is why I stopped at 5H, because we have to stop when you have the last element there. So please, we have done the left coset. So at your leisure time, just go ahead and do the right coset. So the right coset simply means instead of AH, you are going to have HA. So you are going to have HA. The elements of the group will be at the right hand side. That's just the difference. So that's just the difference. So I think you can just go over it again. You have a clearer understanding about this concept. So you have a clear understanding about this concept. Okay. Now let me briefly introduce cyclic group. Cyclic group. So I will introduce cyclic group. Let me introduce cyclic group. You should have understanding about cyclic group. Cyclic group. A group G is called a cyclic. It's called a cyclic group. A group G is called a cyclic group if G is equal to is a generator, that is for all G that belongs to G. So this is called the subgroup. It's called the subgroup of G generated by G. Okay. So when we have some cyclic group, this is how we define cyclic group. Look at just like this sign. This is called a generator. It can generate so many groups. Okay. So this can actually generate so many groups. That is, in other words, let G be a group. Let G be a group. Let G be a group. So if there exists G, small letter G, element in that group, if there exists element in that group, such that for all A that belongs to G, there exists Gn, which is equal to A for some n that belongs to a natural number, then G is called a cyclic group with generator G. So I'm going to use example to explain that better. You understand? A group G is called a cyclic group. Cyclic group if G is denoted as what we have on the board. That unique bracket there. So it is called the subgroup of G generated by that G. So in other words, let G be a group. If there exists G that belongs to capital G, that small G is the element in G in the group. For all A that belongs to G, we can get Gn, G raised power n, which is equal to A. For some n, that n is just a natural number. Then G is called a cyclic group with generator G. So that is that about that. That is, G generates all other elements of G. So it is called generator because it's going to generate all other elements of G. So that's why it is called the generator. Okay. So I'm going to give example now. For example, I'm going to give example now on this. I'm going to give example. Let me give example. For example, for example, the first one where we have integers under addition. So integer under addition is generated by element 1. That is integers. We all know integers under addition is equal to 1. So integer under addition is generated by this. Is generated by 1. So integers under addition is a cyclic group. It's a cyclic group. Integer under addition is a cyclic group. And of course, we can look at this. Just say, let's look, when we say integer under addition, it could be Z2, Z3, depending on the number of elements that we are going to have. Let's take a specific example now. Let's just say for Z5 under addition. So what do we get? When we say Z5 now, it's under addition. We are going to start from, the elements will start from 0. 0, 1, 2, 3, 4. These are the 4 elements that we are going to have. Z5 under addition, that's what we are going to get. So in this case now, what are the generators? Of course, the first one, 0, is going to produce 0. Nothing to add, nothing to subtract. Then the second one, which is 1. Look at the symbol of that generator. This one can actually produce the first one. We can have 1. We can have 1 plus 1. We can have 1 plus 1 plus 1 plus 1. We can have 1 plus 1 in 4 places. Then we can have 1 in 5 places. At the end of the day, that one is going to give us 0. Because we can't get any answer greater than 4 as we have it in the element. So when we look at this now, this is going to give us 1. 1 plus 1 is 2. This is 3. This is 4. Here is 5, but we are under Z5. We're under Z5. So 5 in 5, 1, remember 0. Here will be 0. So we realize that integer, when we have Z5, we are being specific here. Z is not a general integers, but Z5 now, we are being specific. We are being specific here. So we are being specific here. Please check. We are being specific here. Try and understand. When we say integers consist of negative from minus infinity, 0 and positive infinity. Any whole number you can think of is under this integer. Any whole number, just think of any whole number. 1 billion, 500 million, minus 300,000. They are under integers. So when you say integer, under addition, that's the general statement. So for us to be able to explain that is a generator, is a cyclic group, then we are being specific here. That Z5, if I say Z8, it will be from 0 to 7. If I say Z10, it will be from 0 to 9. You understand? So that's what is, this is what is generating. And at the end of the day, this has given us what? Z. This has given us Z5 back. So if you look at the second one also, when it is 2, what do we have? We have 2. 2 plus 2. 2 plus 2 plus 2. 2 in 4 places. At the end of the day, we are going to have 2. This is 4. This is 6. We are under Z5. That will be 1. This is 8. Under Z5, that will be 3. And this is 10. Under Z5, it will be 0. Which it also gives us Z5. So if you continue in that order, you realize that everything will give us the element of Z5. Please, I want you to understand this. I said Z integer under addition is generated by element 1 under addition. But we don't take a specific example now. That is Z5. Please, if you check standard textbook, you are going to understand most of this concept. You know, there is a concept under, we can actually treat natural numbers as a topic. Integers, rational numbers, there are so many properties that they have, and there are so many theorems that actually guide those properties. So when we pick Z5 now, Z5 under addition, what we are going to get here is, we are going to get, these are the elements that you get here. If we start from 0, 1, 2, 3, 4, these are the elements that you are going to get. So it cannot exceed that. It cannot exceed that. This is being specific. So let me just complete this. Then I'll go over it again. Then when we have the third one, 3, it's still the same thing. It continues to generate 3, 3 plus 3. It's not addition. That's why we're adding 3 plus 3 plus 3, 3 plus 3, 3 in 4 places. Then 3 in 5 places. At the end of the day, you realize that we still have all the elements of Z5. Here will be 3. 3 plus 3 is 6. That will be 1. 8, it will be 3. And no, this is 9. Here will be 4. Then here is 16. 16 minus 15. That's it. No, this is 12. Here will be 2. Then here I have 15. Here will be 3. 3 in 3. That's 15. Here will be 0. You realize that this still gives us Z5, the element of Z5. Then the fourth one, when it is 4, when we look at this also, we generate the same thing. 4. 4 plus 4. 4 plus 4 plus 4. 4 in 4 places. Then 4 in 5 places. At the end of the day, you realize that we are still going to have all the elements there. Here is 3. This is 12, that will be 2. This is 16, that will be 1. Then this is 0. We still have Z5, the element of Z5 there. We still have the element of Z5 there. So in this case now, what are the generators here? Apart from that first one, that is 0. 0 is nothing. So we can't get anything. So we can conclude and say thus integer Z5 under addition is cyclic, because we keep getting the same answer. Is cyclic, generated by either 1, when we have 1, we got Z5, or 2 is the same thing, or 3, or 4. Apart from the 0, when we have all this, we are able to get the answer. So that's why I said, okay, somebody is asking that for the generator 2, how do we get 3? And for the generator 2, look at, for the generator 2, you know, you have 2. We have 2 plus 2. 2 plus 2 plus 2. 2 plus 2. Then 2 in 5 places. In 5 places. The first one will be 2. Any number that you get that is less than 5, of course, you write it. The second one will be 4. But when you have 2 in 3 places, that's 6. We are under Z5. So 6 in 5 in 6, you just write the remainder. When we have this now, this is 8. 8 and 5, what's the difference? 3. You write the remainder. Then when it is 10, just 5 will divide 10 2 times. The remainder 0. This is how we generate it. So that's how we generate it. So please, I want you to go over the note again. Just go over everything. It will be clearer. You are going to understand it. So what I've been able to establish the fact that Z5 under addition is a generator, because when we look at it, we're able to get Z5 back in about 4 places out of the 5. It's only when we have 0 that we don't generate it. So integer Z5 under addition could be generated by either 1 or 2 or 3 or 4. That is what is called. I just want to explain that cyclic group further. So that is what we have there. So can I still take one more example? Under coset? So let's take this example. Then after this example, we'll call it a day. So let's take this example. let's take this example. This important example. And after this example, we'll continue from there. Look at it. Let's take this example. That should be example 3. Where we have let G defined as be a cyclic group of order 8. So in this case now, we say G is a cyclic group of order 8, and H is defined as E, comma A4, A raised to power 4, and T is equal to E A squared A quart A raised to power 6. So the first question now, write down Roman figure 1, A Roman figure 1, the left coset of H, then Roman figure 2, the right coset of T. Then the B part of the question now said, what is Roman figure 1? The index of H. Then Roman figure 2, the index of T. Look at what we are given now. Look at G. Let G, G is a generator. A, be a cyclic group of order 8. We are going to see the implication now. So please just concentrate. Please concentrate. You understand the generator that I've been talking about since. Okay. So in this order now, H is given as E. This E is just the neutral element, the identity element. It could be A raised by 0, which is 1. Is identity element. Identity element and A4. And T is given as E, A squared, A quart, and A raised by 6. So look at the question now. Where H and T are subgroup of this cyclic group G. Do you get it? Cyclic group G as 8 is of order 8. You understand? So that is what we have. So the question now says that we should write down the left coset of H, the right coset of T. Of course, once we know the coset, we can find their index. Index is just the uniqueness, the unique element that we have. So now let's solve this. The first thing is that we are going to get G. What is G? So the value of G will now be, is G be a cyclic group of order 8. It's of order 8. So we have something of this nature. This order 1. This is 1. E is like identity element is 1. A raised to power 0 is 1. We have A raised to power. The second one will be A raised to power 2, A raised to power 3, A raised to power 4, A raised to power 5, A raised to power 6, and A raised to power 7. That will be the last one. 1, 2, 3, 4, 5, 6, 7, 8. So G is of order 8, and that's what we're going to have. So in this case now, we know that A raised to power 8 will give us E. That will give us the E. But that's when we are going to get 0. Okay. So back to our first question. A Roman figure 1. We want to find the left coset. So we have to find the left coset, right? We have to find the left coset. The left coset of H are, please let's note H. H is E, comma A4. So the left coset of H, I'm about to list the left coset of H on the board now. I'm about to list that on the board. The left coset of H are E, H. When we say left, we know the meaning. We know the meaning. That is AH is equal to AH, given that H belongs to H. That's what I'm about to list you. Where A is coming from this G. I'll be picking this element one after the other. Then H H is defined as E and A4. So that's what I'm about to list now, so that I don't want any confusion. The first element here is E. EH will now be equal to, we relate it with this. We have EE, comma, E raised to power A4. And what would that give us? That will give us E, identity element, still identity elements, comma, A4. A raised to power 4. It does not have any effect. The second one is where we have A. We are picking all this A, this element A, from all, what we are given now is where we have A. AH will now be, what do we have there? So what do we have there? It has no effect. You view this as identity. A, comma, A raised to power 5. Any question? No? Please look at it. Or let me do it stepwise, please, so that I won't have any, I'm not going to have any problem. I'm going to have AE, comma, A raised to power 4. And that will be A raised to power 5. Any question? Indices. A times A raised to power 4. Look at it. A times A to power 4. Indices. Then A squared of H. We are going to have A squared E, comma, A squared A4. And this will give me A squared, comma, A raised to power 6. Please look at it very well. Any question? If there are questions, you ask so that I can trash it out. This is the first, second, third. We go to the fourth one now. A cube of H. We are going to have A cube E, A cube A raised to power 4. And that will give me A cube A raised to power 7. Then we have A raised to power 4 of H. That will be A raised to power 4 E, A raised to power 4, A raised to power 4. So here I'm going to have A raised to power 4. Please note, A raised to power 4, 4 plus 4 is 8. A raised to power 8 is E, comma, E. That's what we have. Then we go to the next one, A raised to power 5. We go to the next one, A raised to power 5. H will be A raised to power 5E, A raised to power 5, A raised to power 4. Then this will give me A raised to power 5, A. Because A raised to power 8 is E. So E is neutral element. So that's what we are going to have. So please, let's continue. A raised to power 6H. It will be A raised to power 6 E, A raised to power 6, A raised to power 4. So here I'm going to have A raised to power 6 A squared. Then A raised to power 7 H, which is the last element there, will be A raised to power 7 E, A raised to power 7, A raised to power 4. Then I'm going to have A raised to power 7, comma, A raised to power 3. And that's what I'm going to have. That's what I'm going to have. So now let's check the coset. Let's check it out. How many distinct cosets do we have here? E and A raised to power 4. Do we have something like this? A raised to power 4 and E is the same thing. This is 1. A and A raised to power 5. A raised to power 5 and A, this is 2. Then A squared and A raised to power 6. A squared and A squared. Then A raised to power 6 and A squared. This is unique. Then A cube and A raised to power 7. A raised to power 7 A cube. Arrangement does not really matter. So how many distinct cosets do we have there? If you check, how many distinct do we have there? So just say there are 4. You say there are 4 distinct. There are 4 distinct cosets. There are 4 distinct cosets of H in G. Therefore, Roman figure 2. You know, we have to find. The question says that we should find. We have to write down the left coset. We have done that. Then the B Roman figure 1 said the index. So there are 4 distinct. So therefore, so B Roman figure 1, the index of H is equal to 4. Is 4. The number of the same cosets actually defines the index. So I have it on the board. The index is 4. No, the identity element here it will be 1 at the long run. No, the identity element is when you have E, and when you have A raised by 8, and that is what is defined as E in this question. So you see it as 1. You're going to view it as 1. Okay, that's why it does not have effect here. All this E, you know, is order 8. That's why it does not have effect here. Just view it as identity element. You understand? We see it as 1. We are not going to write 1, but you view it as 1. So it does not really have effect on this A. That's why when I said A multiplied by E is still A. A square multiplied by E is still A square. So in this case now, you've just view it as 1, but it's not 1. But from the question, it's of order 8. So once we have order 8, it's going to be 1 in the actual sense. So we have treated the first part of the question. So you can just go ahead. Just go ahead and solve the second one. The second one is where we are asked to find the right coset of T. So just follow the steps. We are going to get the right coset of T. So you follow the step. So let me leave that as exercise for you guys. So I would love to stop here because of our time. We are going to continue from there in our next class. So we have been able to discuss coset and subgroup today. So in our next class, I'm going to start from the order of a group. So we talk about the order of a group, and I'm going to state the Lagrange theorem. So in our next class, it will be interesting. I will try as much as possible to make the class interesting, because these are abstract algebra. So I'm just trying to make it real. So thank you, and God bless you all.